Okay, so quick review of what we covered yesterday. We went over kind of the models of the atom, okay, that are essentially part of the history of the development of our current model. Okay, we started out with John Dalton's solid sphere model. Okay, John Dalton came up with the atomic theory. Okay, those 4 points. All matter is made of tiny indivisible particles called atoms. Okay, the atoms of one element are identical. Atoms of different elements are different. Okay, atoms can combine in simple whole number ratios to form compounds. And in a chemical reaction, atoms can be separated, joined, or rearranged, but not turned into other atoms. Okay, so those were his 4 points. Okay, and then we talked about his solid sphere model and how it kind of fit with the experiments that he had done and all the data that was present up to that point. Okay, then J.J. Thomson came along. Okay, he discovered that there were these small charged particles called electrons. The solid sphere model didn't account for those, so it was modified to become the plum pudding model. Okay, or actually, as we discovered on this year's Physics 30 diploma exam, it is now called the raisin bun model. Because we've been complaining for 20 years that nobody knows what plum pudding is. But you probably know what a raisin bun is. So that's maybe a better way to say it. Because I don't know what plum pudding is. You? So it's the raisin bun model now. We can all modify it. Okay. And then we had, we were talking about that there was kind of a bunch of models that were kind of rejected and everyone kind of arguing about what the atom looked like until Rutherford came along with his gold foil experiment, okay, which proved that there is a central, dense nucleus that is a fairly significant portion of the overall size of the atom, okay, because he had all those X-rays bounce back that he didn't expect. Okay, and then from there the discussion went to where are the electrons? Okay, people thought, orbit like planets, okay, all kinds of different things until de Broglie came along and explained that electrons can't just orbit. They can't be perfect circles. They have to be able to jump around from high energy levels to lower energy levels, etc. Okay, and that could only be explained by this electron cloud, which we're actually going to show is not as random and chaotic as it initially appears. It's actually full of small regions called orbitals, where an electron can be found based on its energy. Okay? And when you get to Chem 20, you'll learn all about these different electron configurations. It's one of the first things you do. Okay? So that's where we left off yesterday, and I think at the very end I showed you how to draw a picture of an atom. Okay? That was how to calculate the number of neutrons. How do we do that? Okay, we use the atomic number. That's the number of protons, the atomic number.
Atomic mass.
Right, you subtract. You go atomic mass minus atomic number. That will give you the number of neutrons. Remember, you have to round that to the nearest whole number. Okay, and then the number of electrons is the same as the atomic number. All right. So the structure of the atom, as we currently understand it, okay, is that there is a dense, positively charged nucleus that contains neutrons and protons. Okay, and there's a large volume of empty space surrounding that contains the electrons. Okay? The position of electrons within that cloud is determined by their energy levels. Okay? The lower energy of the atom, the more of the smaller or closer orbitals will be occupied. The higher the energy, the more of the outer ones will be occupied. And obviously, the bigger the atom, okay, if an atom is really big, it's going to have a lot of electrons and more of the energy levels will be filled. Okay? All right, so this is just kind of a rough impression of what those orbitals might look like. Okay, but you have your nucleus, okay, which would be the central dense part in here. This first purple area is what we call the 1s orbital. It's the lowest energy orbital. Okay, it's where you're very likely to find electrons because electrons are going to be in the low energy level most of the time. Okay, the higher energy orbitals are less likely to be occupied unless the atom's really huge and just has tons of them. Okay, or it's in a high energy state. Okay, so we've got all these different shapes. We got, like we said, the 1s. Okay, we have the 2s orbital, which is also kind of a spherical region around the nucleus. Okay, and then you've got the 2p orbitals. Okay, which look kind of like teardrops or balloons. Okay, then you have a 3s orbital that goes up to 7s, S7p. Like there's a whole bunch of really strangely shaped orbitals that exist based on the energy of the electrons. You don't need to know anything about those for Science 10, just that there's these things called orbitals where you can find electrons, and they're in the cloud. Okay? That's the extent you need to know for this course. Okay, so all atoms are made of the same things. Okay? All atoms are made of protons and neutrons and electrons, but obviously all elements are different. Okay? And the thing we need to remember here is that all elements are different because all elements have different numbers of protons. Okay? It is the number of protons that determines the characteristics of the atom. Okay? So differing numbers of subatomic particles influence the properties of the different elements. Okay? So carbon has 6 protons. It's a solid. Right? Whereas fluorine has 9 protons, and it's a gas. Okay? Everything has different properties because the number of protons is what determines the properties of the atom. Okay, questions so far? So based on what we learned yesterday, okay, there's some questions that I'm going to want you to answer. Okay, give you some time here to do these. They're actually they're on the first page of the chemistry workbook as well. Okay, so there's 12 of them. Okay. They're not terribly difficult. Most of them you just kind of look up in the notes. Some of them will require you to come up with some of your own ideas. Okay, but I'd like to see these answered in complete sentences. I'm going to give you about 25 minutes, okay, or so to get some answers written down, and then we'll go through them together, and you can add anything to your essay that you need to after that. Okay, so like I said, they're in the digital workbook. I'll call that up here as well, just so you can see it. Okay, so this is the worksheet package, the chemistry worksheet package. Okay, and these are the questions that we are working on right now. All right, I'll give you some time to get those answered. Okay, then we'll go through them in detail and then move on to ionic and molecular compounds today. Okay, so question number 1 is asking who first proposed the idea that there are these small, indivisible particles. Who was it? Democritus, okay, the Greek guy. Okay, Democritus came up with this idea first, okay, and it was rejected because at the time the Greeks believed in everything being made of the 4 elements, which made way more sense. It was a much more logical conclusion for them to draw because they could explain the way things worked, the way things were, okay, and so it just was better. All right, so it wasn't that his idea was wrong; it's just they had something that made more sense. Okay. All right, for question number 2, what element did the Greeks believe all matter was made out of? Well, earth, air, water, fire. Okay, why was that a logical conclusion at the time? Those are the things they knew. Okay, and we explained that a little bit yesterday, saying like to make steam, you have to combine water and fire, and that makes water turn into air. Okay, that's steam. So it's some parts air, some parts fire, some parts water. Okay, lava would be some parts earth, some parts fire, and some parts water. Okay, those things would make sense, right? Okay. For question number 3 here, during the Middle Ages, a group of people inadvertently did a lot of work to develop the science of chemistry. They were known as the alchemists, right? Okay, and their goal was to get rich by making lead turn into gold, or the elixir of life, or basically things that they could mix together and get rich off of. Okay, so that's what they were trying to do. Okay, in the late 1700s, okay, a man used the data from many experiments on matter to develop an idea on the structure of matter. Okay, who was he and what were the points of his theory? Okay, who came up with that? Dalton, right. John Dalton is the guy who came up with the atomic theory. Okay, and we reviewed those 4 points at the beginning of class today. Okay, you can put them in your own words, but basically they have to be something along these lines. Point number 1, everything is made of atoms. Okay. Point number 2, the atoms of the same element are identical. Atoms of different elements are different. Okay. Point number 3, atoms combine in whole number ratios to make compounds. And point number 4 is talking about what happens in a chemical reaction. Atoms can be separated, joined, or rearranged, but not altered. Okay, something along those lines. Okay, looking at his idea now, what things do we know of that can prove some of his ideas wrong?
It's based on you can technically split atoms.
Yes, with today's technology, we can technically not only split atoms, we can also fuse them. Okay? In fact, fusion is a natural process that basically gives life to Earth because it's what powers the sun. Okay? So nuclear fission, nuclear fusion both involve altering the nucleus of the atom, hence their nuclear science. Okay? So how does that work? How do we split the atom? Okay, I'm going to tell you how to build a nuclear bomb. Only in very general terms because it's actually quite highly technical. This is just like a bare bones kind of thing. Okay, so what we'd be looking at if we wanted to split the atom in a nuclear reactor, which is a controlled reaction. Okay? In a nuclear reactor, you have things that are called fuel rods. Okay? On those rods are enriched pellets of uranium. Okay? So this is concentrated uranium that's been enriched and made into this pellet form that are stuck on these fuel rods. Okay? When you want to generate electricity with nuclear power, what you do is you lower the rods into the path of a neutron gun. Okay? And this neutron gun basically fires neutrons at the pellets. Okay? Now the pellets are made of uranium, which is a really big, highly unstable atom. When it gets struck by high-speed neutrons, it breaks. Okay? That's fission. The nucleus actually comes apart. Okay? But it can produce a chain reaction if not controlled. That's why the fuel pellets on the rods are very small. Okay? So they get hit by this and they break. Okay? And when they break, the pieces of them also rush off at high speed and hit other atoms which also break. Okay? And this releases a lot of energy in the form of heat. Okay? Since this all takes place underwater, what happens to the water? It gets hot. In fact, it boils. The steam then turns a turbine and will generate electricity using nuclear power. Okay? If this goes bad, then we have problems, like Chernobyl. Okay? What basically happened in Chernobyl is the fuel rods became locked in place and were not able to be removed. Okay? And so the fission process continued even though the neutrons were no longer being fired, okay? And the whole thing overheated, causing a meltdown. Okay? Basically meaning the concrete walls of which the nuclear power plant was made got so hot that they essentially melted, and then radioactive material was released into the environment. Okay? And that whole place is still radioactive. Okay? They have this big thing, I don't know if anyone's seen, they had a big documentary on it. It's called the elephant foot. It's basically the pieces still of the melted fuel rod. They're still not only radioactively hot, but thermally hot as well. Okay? And it looks like the foot of an elephant. It's this kind of blob of half molten metal that used to be the fuel rod chamber. Okay? That's still kind of glowing. Right? And if you stay around it too long, you'll glow too. So that's how a nuclear reactor works. It's a controlled reaction. If we want to generate less electricity, we simply remove the fuel rod from the path of the neutrons, and the fission process slows down, okay? And the water then doesn't boil as much. Okay? In a nuclear bomb, we want an uncontrolled reaction. We want a chain reaction that gets crazy. Okay? So what we do is we put a big lump of fissionable material, plutonium, uranium, something like that, in the center of the bomb, and we surround it with a shaped explosive charge. Okay, so this entire shell would be made out of like C4, plastic explosive, something like that. Okay, and essentially all we do is detonate this explosive, conventional explosive, and the pieces from the explosion, the debris from the explosion, are focused inwards onto this piece of fissionable material, which then starts a chain reaction. Every little bit, every atom in here that splits has pieces of itself that hit other atoms that split, and chain reaction happens, and you get a big mushroom cloud and destruction and death and all that other stuff that goes along with a nuclear bomb. Okay? In theory, building one is very, very easy. In practice, it's very much not so. Okay? It's much more difficult than what I'm laying out, but this is essentially how it works. Okay? So we have these atoms that can be split. The bigger an atom is, generally the less stable it becomes and the more useful it is in this kind of an application. Nobody tries to split lithium atoms in a nuclear reactor. Okay? They're really, really small, so they're not a big target. Okay? And secondly, because they're small, they don't have a lot of energy when they break. The bigger an atom is, the more energy it releases when it breaks as well. Okay? That sort of makes sense? Yeah. All right. Now, the fusion thing, okay, is a little bit different. In fusion, atoms are forced together to form a new atom. Okay, so in the sun or in a fusion bomb, okay, what happens is hydrogen atoms are forced together under extreme heat and pressure until they form a helium atom. When that happens, the nucleus is changed and energy is released. Way more energy is released in fusion than in fission. Okay? Fission is actually highly inefficient compared to fusion. Right? Either way, the nucleus is altered, and when the nucleus is altered, energy is released. Okay, that's what we need to get kind of out of that. Okay, so describe in your own words the model of the atom discussed here. So basically, all I was looking for on this question was for you to talk about the solid sphere. Okay, that it kind of fit with what they knew. It accounted for atoms being able to be separated, joined, and rearranged in a reaction, and that was really all it was meant for. Okay, the plum pudding model was developed to account for moving charges, electrons. Okay, the Rutherford or the nuclear model was developed to account for the results of Rutherford's experiment. Okay, showing that yes, there is a central dense area surrounded by a lot of empty space. Okay, and that the de Broglie model was developed to account for both the idea of the nucleus as well as the idea that electrons can move around and jump to different energy levels. Something along those lines. All right, as our knowledge increased, we discovered the atom had smaller parts. So name these parts, describe them, and tell where they are located. All right, so the parts are protons, and they are where? In the center, called the nucleus. Okay, so we got the nucleus, okay, and then we have, sorry, what's the charge on a proton? Positive. Okay, we have electrons, okay, and they're located in the cloud, and they are negative. Okay, and then we have neutrons, are neutral, and are also in the nucleus. Okay, that's really all you need to know. Okay. Okay, number 8. If I have 1 cubic centimeter of lead and 1 cubic centimeter of carbon, the lead is way heavier. Why would that be?
Because of the atomic mass.
Yeah. The atomic mass of lead is greater, and that means that lead atoms are bigger and heavier. Okay? I mean, if we look at our periodic table, remember that a carbon atom has 6 protons and 6 neutrons and 6 electrons. Okay? A lead atom, okay, is much bigger. It's 82 protons. Okay? And 100 and I'm not doing the math in my head. A lot of neutrons and 82 electrons. Okay, so yeah, we've got a much bigger atom. So if I have equal numbers of lead atoms and carbon atoms, obviously a big chunk of lead is going to be a lot heavier, simply because the atoms are bigger. Okay, right, we talked about number 9 already, nuclear reactors splitting large nuclei of uranium atoms. Okay, so why wouldn't we use less dangerous, smaller atoms? We talked about that as well. If they're smaller, they don't have as much energy and they're harder to hit. Okay? Hitting a uranium atom in a nuclear power plant is like putting a bullet through the side of a barn. Okay, but and from like 10 feet away. If you're trying to hit a lithium atom, that's like trying to split a hair at a mile away. Right? You're not going to do that. Okay? It's just a smaller target. Okay. Atoms are indivisible. Why was this statement believed for so long? Why is it still somewhat true provided no human technology is present?
Because even today, like, you still need super precise and super thin and sharp things to split the atom, so it's still technically impossible without a machine helping you with that.
Yeah, in fact, not even so much thin and sharp as it is we have to have something that can shoot subatomic particles at other atoms, okay, in order to make this happen. That's high technology, okay? Now, are there some atoms that break down on their own? There are. Okay? Anything that's radioactive is breaking down on its own. It's actually undergoing this kind of fission process naturally, but at a very slow rate. Okay? Even something like uranium, okay, it's radioactive. It's bad for you. You wouldn't want to be, hanging around with it all the time. Okay? But at the same time, it radioactively decays very, very slowly. We accelerate that process in a bomb or in a nuclear reactor. Okay? But on its own, it would naturally break down into other materials slowly over the course of hundreds of thousands of years. Okay? We obviously want that to go faster. Okay? But it does happen on its own with some materials. Okay? And you have to be careful of those materials. They're radioactive. Okay? This is what killed Mary Curie and Henri Becquerel and people that discovered things like X-rays and gamma rays. Okay? They studied these radioactive rocks. Now, at the time, they didn't realize that this stuff was very bad for them. They kept these rocks in their desk. Okay? They worked at their desk. Like Henri Becquerel's desk is in a museum in France, and it's still, if you put a Geiger counter, those things that read radiation and make the ticking sound, next to his desk, it still goes crazy. This is a desk somebody sat at and worked 100 years ago. Okay? So obviously he didn't live very long. Okay? Unfortunately, the people who discovered all this stuff had very short lives. Okay? Because they died of cancer, right? Because they were constantly being exposed to these things they couldn't see. Right? We can't see radiation. Okay? They just came home from work every day feeling sick. Right? They didn't realize they were getting radiation poisoning at work by playing with these magic rocks. All right. Okay, from what you know of the structure of the atom, why does it stay intact? Okay, why do the electrons not fly off or the protons separate from the nucleus? What holds everything there?
How to explain it?
You're on the right track.
I can't explain it, but so the protons are attracted to the electrons, and so then they want each other, and then keep them going in a circle. You better explain.
Yeah, okay, right, you're on the right track though. It is an electromagnetic force, okay, that exists within the nucleus of the atom. Okay, electrons don't fly off because they're attracted to the protons in the nucleus. Okay, now the protons in the nucleus are as positive as you can be. They're surrounded by neutrons, which are neutral. But when you're extremely positive, something that's neutral would seem negative by comparison. So there's these interatomic forces or internuclear forces that hold the protons and the neutrons together in the nucleus of the atom. Okay, so it basically has to do with like things attract or repel and opposites attract, and there's a lot of attractive force, okay, within the atom. Okay, and we talked about number 12 yesterday as well with photosynthesis and glow-in-the-dark materials. This has to do with electrons being able to reach higher energy levels, and then when they come back down, they release that energy, and that energy can be used to do useful things. Like it can be given off as light, so glow-in-the-dark material will glow. Okay, for a plant, that energy can then be used to break apart carbon dioxide molecules and water molecules and form them into sugar. Okay, if you're looking at a similar process within your body, okay, the fuel for your muscles and all of your cells is something called adenosine triphosphate, or ATP. Okay, and electrons can kind of fall down this energy staircase that involves them giving off their energy to your cellular processes, okay, through this molecule. Okay, so the electrons become excited, okay, and their energy can be released as they fall down, okay, allowing your body to build proteins and do whatever it needs to do. Okay. All right, questions on any of those? Okay, this is the kind of stuff that's probably going to appear on Thursday's quiz. Okay, so this would be the thing you would want to study for Thursday's quiz, the notes from this lesson and your answers to these questions.